right, so for the first one, if p is a polynomial of degree n, where n is greater than 0, what is the degree of the polynomial? Q of x. If q of x is defined as the integral from 0 to x of p of t dt. So we know that q is a polynomial function, and we are trying to take the integral of a polynomial function. So remember, another way of defining an integral is taking the antiderivative of that function. So if I'm looking at q of x equaling the integral from 0 to x of p of t dt. So we would take the antiderivative. Since I know q is a polynomial function, the antiderivative of that is taking, if you remember, adding 1 to the exponent and dividing it by the new exponent. So I'll give you an example. Let's say if f of x equals x to the 5th, then the antiderivative, we'd say capital F of x, is going to be x to the, we have to add 1, so we could write it as 5 plus 1, but then we have to, in front, take the coefficient, whatever the coefficient is, in this case is 1, and divide it by the new power, so in this case 6, because when we were to, if we were to check our work and take the derivative of that, we would have, let me simplify this, so you have 1/6 x to the 6th, we'd have to multiply that to the front, and so we want the 6 to cancel out or to reduce the coefficient to 1, so we have it up there. So the point is, we take the power, when we're taking an antiderivative, we take the power when we add 1 to it. So the question is, if p is polynomial with a degree of n, okay, then its antiderivative would have what degree on it? Well, if p is written, I guess you could say p of x is written as x to the nth with whatever coefficient plus whatever else at the n, then q of x would be something, let's do this, a of x to the n, then q of x would be something times x to the n plus 1. And it doesn't matter what that something is. I mean, if you're going to figure it out, it'd be a over n plus 1. But that's not the question. It says what degree of polynomial. So the degree of q of x is just n plus 1. It's got an n plus 1 degree because its derivative has a degree of n. Okay. Number 2, it says dy dx equals 1 over x. And we're looking for the average rate of change of y. Now, there's a couple different ways to go about this, but hopefully we can make a connection between the idea of average rate and average value. They are related. They're not the same thing, but they're related to each other in comparison. So if dy dx equals 1 over x, and we're looking for the average rate of y, well, we need to know what y is, in theory. So we, in order to get to y, if I'm given dy dx, remember this is another way of saying y prime equals 1 over x. In order to get to y, we take the antiderivative. So the antiderivative of y prime is y. The antiderivative of 1 over x is the natural log of x. And we're going to get to an understanding later on that it's actually the natural log of the absolute value of x. But we don't need that right now. So that's y. Okay? And we're looking for the average rate of change of y. The average rate of something is its slope over that interval. So we would figure out y2 minus y1 over x2 minus x1. In this case, the interval is from 1 to 4. So we're going to figure out y of 4 minus y of 1 over 4 minus 1. That's the average rate of y because we're taking the slope of y. Okay? So we just plug in those values. So you get natural log of 4 minus natural log of 1 over 3. Fair enough. Now, how you write this and how far you go with simplifying depends on whether it's a multiple choice question or what form the professor or the teacher might want. We can simplify the natural log of 1 to be 0 because e raised to what power gives you 1 is 0. So we could rewrite this as the natural log of 4 over 3. The multiple choice question that I got this from does not look like this. The answer doesn't. None of the answer choices match this. So we have to know our rules of logs. Well, the rule of log, we can rewrite 4 as a power. So we can say natural log of 2 squared over 3. And then there's a rule of natural log. It says you can bring the power out front, so we could rewrite this as 2 natural log of 2 over 3. So any one of these answers is valid answers. Just depends on what the form of the final answer is what you're looking for. So that's that. That's one way of approaching how to find the average rate of y. But another way to look at this, and this is a good way, this is a decent way of looking at this, is to look at it in terms of the average value. Now I'm going to make a connection here. The average rate of f of x would be over the interval over a to b can be written like this: f of b minus f of a over b minus a. That's basically what we did here. We took the average slope between a and b of the function. If we look at average value, well, average value of f over a to b would be written like this: 1 over b minus a times the integral from a to b of f of x dx. Now, these are not the same thing, but if I rewrite something just a little bit, it actually ends up being the same thing, and here's why. Okay? In order to evaluate this, we have a definite integral here. So what we need to do is take the antiderivative of the integrand. So we'll call the antiderivative capital F. So we would write this as capital F of x evaluated from a to b. And then after we're done with that, we're going to divide it essentially by b minus a here. Okay, so because 1 over b minus a is the same as dividing by b minus a. So we'd have to ask ourselves, what is the antiderivative of f? We don't know. But if I just change one thing on this, it actually makes sense to match this. If I put a little prime there, if I want the average value of f prime over a to b, then it would look like this. Okay? It would be 1 over b minus a times the integral from a to b of f prime of dx. Well, that's important because when I go to evaluate this, what is the antiderivative of f prime? Well, the antiderivative of f prime is f of x evaluated from a to b. And then we can put that over b minus a. And so when I go to evaluate this, I end up with f of b minus f of a over b minus a. And you can see that that matches the average rate. Now, take a minute and let that sink in a little bit, because that's really cool. That's a cool connection. That's an important connection to make here. And if you listen to these words here, okay, we're saying the average rate essentially is equal to the average value of the derivative. The average rate of f is the same as the average value of f prime. And here's why. If you take the rate of f, if you think of just rate, the rate of a function is its derivative at every point. So f prime is the rate. So we could rewrite, or we could rephrase this statement as the average value of the rate of f. The average value of the rate of f. Or the average rate of f. The average rate of f. So you can see that this equation here is the same, actually, as that. So we can go back over to number 2 and rewrite it that way. If I want the average rate of change of y, that would be the same as saying the average value, so 1 over 4 minus 1, the average value of f prime. Well, in this case, it's dy dx. So it's 1 over x and then dx. This is the average value of dy dx. This is the average value of the rate. Therefore, it is the average rate. So we would evaluate this as 1 over 4 minus 1 times the natural log of the absolute value of x, like we talked about before, evaluated from 1 to 4. Now I'm going to put this in parentheses because I want to do that first. So you end up with the natural log of 4 minus the natural log of 1 over 4 minus 1, which was the same thing as what we had before. But that connection needs to be made in the brain. You got to let it sit and marinate for a little bit, because you need to understand that the average value of f prime is the same as the average rate of f.